Hello, I'm Wilson, and this is Isaac, and
Hello.
we're doing heroin in adolescence. So our question was, can we determine the amount of heroin taken by an adolescent depending on how high they appear? So a bit of background on what exactly heroin is. Heroin, or deacetylmorphine, is an extremely potent opioid developed by a drug company in the 1800s. And the powerful effects of heroin are attributed to the fact that some of its byproducts, its metabolites, are also contributing to making the user high. So heroin and two of its metabolites, 6-MAM and morphine, those three combined effects make adolescents high, or anyone that takes it. So in our stock and flow diagram, we basically have brain heroin is affecting 6-MAM and 6-MAM is affecting morphine. The reason why they're like sources right here is because technically these are not the same thing. So in reality, it's like as if it's coming from another source, and this is positively affecting it. So when we are modeling when we were modeling these three concentrations in the blood, we used half-life because heroin, 6-MeM, and morphine have well-established half-lives, which can be used to find a differential equation, right? So our first differential equation for heroin is basically constantly decreasing because it's a bolus input from the fact that most of the time heroin is taken through an IV. And when we go to this next equation, which is 6-MAM, it's simply the output from this heroin into this one minus a change depending on its half-life. And then the morphine is basically the 6-MAM output minus a certain output depending on its half-life. And then we found the established values, and then we calculated for what the coefficient should be here. And now Isaac will talk about the graphing work and our data.
All right. Here we have our time series of the three compounds. We have our heroin, our 6-MAM, and our morphine concentrations. From this time series graph, we can see that our general behavior is correct because first we have the heroin bolus input decline. Then soon after, we have a short delay, which has a 6-MAM peak. And then we have another short delay with the morphine having a peak and going off. From this graph, we can also see that the half-lives are as we expect, so that kind of validates our behavior. We can go on to validate the values by looking at these graphs of our model versus real data we've collected from a 2012 study. We can see for heroin, we have almost the same trend, while the real data is a bit steeper. And also for the two other graphs, we have similar behavior, but a little bit of a difference in the slope. From these time series graphs, we came up with this graph, which shows relative highness of a student based on their body mass and the time since injecting heroin. So we can see that in this red section, which represents definitely high, these students are in the lower body mass and have a short waiting period after taking heroin. So these people are definitely high. In the yellow section, they have waited more time, so they are questionably high. And then finally, in this green section, these students have experienced a long time after taking the heroin, so they are not high. In conclusion, we can see that this model helps us do some work by, for medical professionals, they could examine students and based on their body mass and behavior, they could infer the amount of heroin that was taken. And this would help them come up with a course of action in order to help these students. And then we still think we could have some improvements for our model. First, our stock and flow is a bit simplified. Although it is generally correct, it could include some of the more subtle flows in the human body. And as well, our calibration of highness could be tuned more. We've used data from studies, but we could find more in order to improve it further.